Alright, I'm going to take you through how to calculate the reaction forces for our example truss here. So the first thing we're going to want to do is we're going to want to turn this little sketch that we have into a free body diagram. So what a free body diagram does is it frees all of the forces and members from the body. And so in this case, we have just a simple truss. We're representing that with a simple geometric shape, in this case a triangle. And so what we're going to do is we're going to make some labels on it, and we're going to put some forces on it so that we can see the reactions from the applied forces. And so the first thing we'll do is we'll label all the points on our triangle. I'm going to label this point over here A, and I usually just work from left to right and label my points. I'll label this point B, and I'll label this point over here point C. Okay. The next thing that we can do in our free body diagram is we can graphically or draw and represent the forces. And so if I look at this diagram here, we have a force of 100 coming right down on point B. And so I'm just going to go ahead and label this as F for force. Now, that's our applied force to our free body diagram. We're going to need to illustrate the reaction forces now. And so over here at point A, I have a pinned connection. A pinned connection supports that point in two directions. And so I'm going to have two reaction forces. And so because this force, the applied force, is going down, our reaction force at point A in the y direction is going to be up. And so I will draw in that force there, and I'll label it R for reaction at A in the y direction. Alright? Because this is a pinned connection, we do have two forces, so I'll draw the other force out from it. This is the reaction force at A, in this case, in the x direction. Because it's a pinned connection, we have both those forces there. If we look over at point C, we have a roller connection. It's only supported in one direction. And so at point C, we have simply one reaction force, and it's the reaction force at point C in the y direction, or RCY. Right? The other thing that we need to do in our free body diagram is we need to have some dimensions, so we know how large these sections of our truss are. And so I'll go ahead and sketch up a line. And I'll sketch up a line from point C. And I'm going to go ahead and label this dimension between point A and point B, not the length of AB, but the distance in the x direction, as 7 inches. And I'll add a dimension line to that. All right. Now from B to C in the x direction, it's going to be 3 inches. We have our angles already given to us. This angle right here at point A is 45 degrees. So I'm just going to draw that in so you can see it a little better. And this angle at point C is like about 66.8 degrees. And again, I just draw those in so you can see them a little better. All right. And so to solve for our reaction forces, the first thing that we are going to want to do is figure out what the reaction forces are. We've labeled them. There's 3 of them. And so the first one we want to solve for, I always start from the left and work my way to right, and I always solve for y direction reaction forces before I solve for x direction. And so I'm going to say we're going to solve for RCY, or excuse me, RCY first. And so what we're going to do when we solve for RCY is we are going to use our moment static equilibrium equation to do that. You could use vector addition to do this, except we don't have enough information to use vector addition, and so we're going to have to use the moment static equilibrium. And so if I take the sum of the moments about point A, those have to equal 0 in order for our truss to work. All right? And so now we need to figure out what those moments are. And so the first moment that we have is we have the force at point B times the distance back to point A. And so I'm going to say the force at B times 7 inches. So we're going, again, we're starting at point A, so everything's going to go back to point A, plus RCY, that's another force in the y direction, times the distance back to point A, 10 inches. That has to be equal to 0. So I can plug in my force at B. Because the force is going down, it's negative. And so I'm going to say negative 100 pounds times 7 inches plus the reaction force at C in the y direction times 10 inches for that moment have to be equal to 0. Multiply these two, and I get negative 700 inch-pounds plus RCY times 10 inches equals 0. We're working to get RCY by itself, so I'll add 700 inch-pounds to either side of my equation. And I get reaction force at C in the y direction times 10 inches is equal to 700 inch-pounds. Now to get RCY by itself, I'll divide both sides by 10 inches. Inches cancels out, and I get RCY is equal to 70 pounds. And so what that tells us is that if we put 100 pounds at point B in our system here, the reaction force at point C here is going to have to be 70 pounds. And so I'll go ahead and write that in on my free body diagram, and I'll circle my answer. Alright, so I have RCY solved for. Now I need to solve for the other force in the y direction. And so this one is RAY. And so over here I'll write that I'm going to be solving for the reaction force at A in the y direction. Now this time I don't need to use the moment equation because I know RCY and I know the force, the applied force at B. So because I know those two things, I can solve for RAY. And so I can use the sum of the forces in the y direction. They have to equal 0. And so that's our static equilibrium equation. We know that. All right? And so then we will simply input our forces in the y direction. So our forces in the y direction, just moving from left to right, are the reaction force at A in the y direction plus the force at point B plus the reaction force at C in the y direction, all of those things have to equal 0. Alright, and so now we can plug in some numbers. I don't know RAY, the reaction force at A in the y direction. I know the force at B, the applied force. Again, it's negative 100 pounds because it's going down. And I know the reaction force at C in the y direction. It's 70 pounds. All of those things have to equal 0. So I can simplify my equation now. So I have RAY minus 30 pounds equals 0. I'll add 30 pounds to both sides of my equation to get the reaction force at A in the y direction, and that will make it equal to 30 pounds. And so the reaction force at A in the y direction is 30 pounds. And so again, if we're putting 100 pounds of force at point B, we get a reaction of 70 pounds at point C and a reaction of 30 pounds at point A. Which makes sense because the force at B is closer to C than it is to A. All right? The last thing we need to calculate are the reaction forces at A in the x direction. And so if we're solving for the reaction forces at A in the x direction, we could use the same system. Sum of the forces in the x direction have to be equal to 0. Our forces in the x direction, we don't have any, so the reaction force at A in the x direction has to be equal to 0. And so the reaction force at A in the x direction is 0 pounds. All right? So that's how you solve for the reaction forces with a free body diagram.